If you asked me to name one idea that cuts across the fields of science, technology, engineering, and mathematics, I would choose a simple and elegant concept developed by a man named Joseph Fourier, the Fourier transform. It pops up everywhere: sound, heat, light, genetics, medicine, music, movies. It's even being used by your own eyes, ears, and brain as you watch and process this very video. So how do we begin to understand this far-reaching yet fundamental concept that is at work all over our universe? Well, we'll start with a circle and some triangles.
Let's draw an xy coordinate plane and a circle with the center at the origin. Our circle has a radius r of unit 1, from which we drop a perpendicular p, creating a right triangle with an angle theta. The sine of theta is equal to the opposite divided by the hypotenuse, or p over r. In our case, r is 1, so the sine of theta is p.
Let's rotate r like the hands of a clock. As angle theta changes, the length of the opposite side p also changes, becoming really small as it approaches the x-axis and becoming its largest when it approaches the y-axis. Now imagine sliding our paper from underneath our pencil as we trace the height of p as it oscillates from its largest to smallest value. We begin to draw a wave that looks like this. This paper sliding technique is a little tricky, so I made an animation in PowerPoint. The wave we're drawing is called a sinusoid, and it can be graphed with the function y equals a times the sine of omega t plus phi, but don't let this equation scare you. A is the amplitude, or the height of the wave. Omega is the frequency, or the pitch of the wave. Phi is called the phase, which can shift the wave left or right. Fourier discovered that you can replicate any shape simply by representing it as a sum of such sinusoids. If we add enough sinusoids, we can even create straight lines with sharp corners like this square wave. So you may know that sound is a type of wave. We can learn about the Fourier transform through one of its many applications: music.
If you've ever created or listened to an audio recording, you might have seen a waveform like this one here. So, how do we store this sound as a digital file, such as an MP3? The answer to this question is a bit more complex, but we can use what we have learned so far to understand a more simplified version of the process. Remember, Fourier discovered that any function can be written as a sum of sinusoids. That means that our waveform can be written as a sum of n terms, like this. Each sine term has an amplitude a sub n, a frequency omega sub n, and a phase shift phi sub n. We can extract the coefficients or amplitudes a, the frequencies omega, and the phases phi, and construct a table. This series of numbers can become a digital file, such as an MP3. Our file can be transmitted via the internet or saved on an electronic device. If we would like to compress or reduce the size of the file, we can reduce the number of terms. Now, how do we convert the digital file back into sound? At this point, all we need to do is use these numbers to do an inverse Fourier transform. That is, use the values we extracted to recreate our initial waveform. Now we can listen to our recording. The more terms we originally included in the file, the higher the quality of the sound. Let's go back to the table we made to explore another application of the Fourier transform: music editing and auto-tuning. We use this when a singer sings off-key. We can plot the amplitude and the frequency values to create a graph, like this one. We have now plotted our waveform, which used to be a function of time, as a function of frequency. Now we can do things like noise cancellation or auto-tuning by removing or shifting certain frequencies. Using what we've learned so far, we can imagine how to use the Fourier transform to represent digital images and videos. You may already know that light is a wave and that color is related to the frequency of such a light wave. If you think about it, any image can be broken up into little dots, and each dot can be represented by a color and an intensity. In other words, frequency and amplitude.
Fourier's ideas have already changed the ways in which we view the world, and the Fourier transform will undoubtedly continue to make waves in our unending pursuit towards uncovering the secrets of the universe.